Piezoresistive polymers have been used in sensors for human motion tracking and shape sensing, and they are usually interfaces using wires to transmit the data. However, the difference on the stiffness between these two materials can cause issues such as stress concentration that can reduce the life cycle of these sensors. I am Leonardo García-García from the Sensor Technology Research Center, and I'm going to talk about copper wire-based electrical contacts for the interfacing of stretchable sensors. One of these applications that we have is the human motion tracking that you can see in the figure, and we use the wires to transmit data. It doesn't matter what kind of contact you are using, you have to use wires to transmit the data. And the wires are usually attached using flexible contacts pasted with conductive epoxy or silver paste. However, the difference on stiffness between these materials can render sensors inoperative, reduce the life cycle, and can make them really unusable after a few cycles, which is not ideal for any application where we want to increase the lifespan of these sensors. Therefore, that's why we decided to try different copper wire-based cables. The first one is the filament cable that we have here, which is formed by 8 ultra-soft wire cables of 0.06 millimeter diameter and a core of which is made of fiberglass. It's worth mentioning that this interface is really flexible and is usable almost like a strand and is any yarn that you can have. Also, we test the multi-strand cable. It has 8 strands, which are 0.18 millimeters of thin copper wire. Also, this flexible wire is long. It's also rigid, so it's not really a good option for small sensors, but can be worked for big sensors. The next option is copper wire, which is 0.15 millimeters, which is thin, flexible. And also we have the same copper wire, but covered with yarn. As we know that yarn and textiles have strong adhesion with Ecoflex. The yarn can provide strength to the interface. And also we have copper mesh here. The copper mesh we decided to test also is rigid, the same as the multi-strand cable. We decided to test them because the mesh can be fully enclosed in the material, and we can have strong adhesion to the material. And that's why we decided to test this one, which is soldered to a copper wire. To test to test the interfaces, we have 2 different configurations. The first one is the sensing polymer fully encased in a cylindrical case container with some support at the bottom. The support at the bottom has 2 holes where the wire interfaces passes. And the load was applied to failure, which was affecting only the interfaces. Also, to test the strength and the drift of the resistance, we performed 1,000 cyclic load tests using 20, 40, and 60% of the total load at failure. As you can see here in the figure, we decided to add the load to only one side of the interface using a motor. The motor will control the loading and unloading of the load, so we don't have free load. The motion will be controlled by the motor. Then the second configuration that we use is a sensor, as we have been using for our applications. But the sensors we use silicone handles at both ends of the sensor. Why? Well, because usually when we test the sensors, we just clamp both ends of the sensors and we start to test for strain cyclic test. But in the real applications, you don't clamp the ends. You just attach the sensors where you want to measure, but the contacts of the ends of the sensor where the contacts are free. So we decided to have this configuration, this one. And from the results, we observed that the maximum load supported was for the yarn cover wire, as we expected, because it has a high energy, high adhesive energy, the second with the yarn. The second one is the filament cable, followed by the multi-strand and the mesh. And unsurprisingly, the lowest in strength was for the single wire. For the stability, we measure the resistance throughout the whole loading test. We measure the initial resistance, and here I present you the initial resistance and the resistance before break, the maximum resistance before break. Here, and you can see the lowest contact resistance that you can have is for the multi-strand cable and the mesh cable, as we expected, because they have higher surface area. But the yarn cover wire, despite of having higher strength, has the lowest contact resistance of all, which is something that we did not expect. For the stability also, we measure the change in resistance during the whole loading test. And as you can see here, the more stable is the multi-strand, followed by the mesh. The mesh only has like a small variation by towards the end of the test. The third one is the filament cable, which has like a small variation, also has small changes in the resistance during the whole test. They are small, but this increase after the 60% of the total load applied. In the variation, you can see high change in resistance. And the yarn cover wire also have like huge variations in resistance, as you can observe here. One single wire didn't support the high loading, and the variation resistance is really high for the small load that it supported. Then we decided to have the 1000 cyclic test to measure the drift. And here I'm only presenting you with the best option, which is filament cable, and the second was yarn cover wire. As we expected, the single wire didn't stand not even 3 cycles test because the poor adhesion that it has. But here we observe that the yarn cover wire supported 2 tests for 20 and 40%. And we have, although it has a high, you can see the change in the drift for 20% of the load. The changes at 40% is small, only increases toward the 1000 cycle. The drift, there is a huge variation in the drift, right? But then it only supported 500 cycles at 60% of the load, contrary to the filament cable, which supported the whole test cycles. Also, it has huge drift for the 20% of the maximum load. For the 40 and 60%, the drift is really small, as is observed here. And also, the behavior of this filament cable can be observed here in the application where the sensors are. So for the real application, we did like this strain test from 0 to 50%. And we observe here, we increases the strain in steps of 10%. And you observe here that although it was only one test, one linear test, you can clearly see the different behaviors of all the interfaces here. The most linear was the multi-strand, but it has a small percentage change in resistance. But for the filament cable, you can see a linear behavior, almost exponential, between 20 and 50%. Although it's high, that means the it has high sensitivity. So the high sensitivity is required for some application we have more than 10% strain, which can be seen as a good point here. Well, for the conclusion, we tested the 5 different options that we have using copper wire. The multi-strand show better stability and lower contact resistance and can be used for large sensors. But for smaller sensors, it will really reduce the flexibility and also can increase the chances of having stress concentration on soft material, which is not ideal in any application. We also observed that the yarn cover wire showed a high bonding energy, but this one was mainly due to the yarn. So if you want an interface that has a higher strength, you can use yarn, and you can combine with any other one. And the best performance was for the filament cable because it has the second highest strength, had also good stability up to 60% of the total load, and also it was the only interface that could withstand the 3 cyclic tests on the 20, 40, and 60% of the total load, and the drift was really small. It's worth mentioning that this filament is almost flexible as a yarn, is very flexible, and the effects of having a stress concentrations is really small. We also think that the strength of this sensor could be due because of the fiberglass in the core of the filament. And as a future work, we plan to use a combination of interfaces for contacting piezoresistive polymer sensors. We might use filament cable covered with yarn to increase the strength and to secure a low contact resistance. This was my presentation, and thanks for listening. Now, if you have any questions, feel free to ask.